Assalamualaikum warahmatullahi wabarakatuh in a very good day. I hope everyone is doing fine in this difficult time. Today I would like to present about my final year project, which is the development of customized Uncle for orthosis A4 with IoT controller. Before that, I would like to introduce myself. My name is Abdul Muqtadir bin Wahid and I am the under supervision of Dr. Abdul Halim Abdullah. Start my presentation with the project summary. In the beginning of this project, I will focus on mainly of 2 points. The first one is a study of the complication of bedridden patients such as muscle weakness and muscle shortness. Second point is the study on the existing ankle for orthosis, which is a device for rehabilitation that have been exist many years ago. This 2 point is very important because it helps me to achieve the objectives of the study, which is to develop a customized AFO for bedridden patients to avoid muscle shortness and muscle atrophy. Now, for the introductions. Bedridden occur when a patient or a person's experience stroke, cerebral palsy, head injury, or spinal cord injury. So, due to this bedridden, many complications might occur. One of the serious complications that might occur that related to muscle is the muscle atrophy and muscle shortness. While for AFO is a device used for rehabilitation process. A common patient that use AFO is a stroke patients. They use this AFO to assist the stroke patient to walk. Most of the AFO is rather expensive, complicated, or is not suitable for bedridden patients. But most of the existing AFO for bedridden patients is rigid and is fixed at 90 degree angle. Hence, this project is to develop a customized AFO with IoT application, which is to control the movement of the ankle joint to avoid muscle atrophy and muscle shortness, especially on the calf muscle. Now we will look at the problem statements. As I mentioned before, the main study of this project is on the bedridden patients and on the AFO. The problems that can counter the muscle atrophy and muscle shortness on the calf muscle is by using an AFO device. But there are problems due to this AFO device. First of all, AFO OLED support for bedridden patient is fixed with 90 degrees. So the muscle will not move and the muscle will stay still because it have no ankle joint movement. Second, most of commercial AFO only applicable to assist patient with drop foot and gait conditions. The third one is the existing AFO is complicated and expensive. Now, in this project, there are three main objectives that needed to be achieved. The first one is to design a customized adjustable AFO. The second one to analyze the strength of the AFO at different parameters. And the last one is to fabricate the customized AFO using 3D printer with the integration of remote control, which is by using the IoT application. First, the scope of work will involve by designing the product of the AFO using a CAD software, which is CATIA V5R20. Second, after the product has been designed in the CAD software, the same CAD software, which is the CATIA V5R20, will be used to conduct a static analysis. Now, two different values that need to be taken in this static analysis, which is the von Mises stress and the displacement. We have three different parameter settings in the static analysis. The first one is by using three different materials. The second one by using three different thickness, and the third one by applying variation of load to the FO. Now the FO will be fabricated using a 3D printer. The next one is by developing coding using Arduino IDE. This is because we want to control the ankle movement joint so we can avoid muscle atrophy and muscle weakness on the calf muscles. Hence, by using a coding which will be inserted next to the microcontroller MCU, it can give instruction to the external device that will be inserted or will be put on the AFO that can control the ankle joint movement. In this project methodology, I will explain the entire process starting from the beginning of this project until at the end of the project in order to achieve all three objectives. Now, first of all, we will identify the problem identification. This process has been taken during the FYP 1 last semester. After all the data have been taken about the bedridden patients and the current AFO, all the idea and the idea was set will be generated and filtered by using PARC method. Then the final design will be designed in detail in the CAD software. Now, after this has done, then the objective number 1 has been achieved. We will move on to the analysis, which is the main part of the objective number 2. So the analysis will be conducted with 3 different parameters as mentioned earlier. After the analysis have passed, the project moves to the product fabrications, which is the AFO will be fabricated using the 3D printer. And then this is where the IoT application begins. It begins firstly with design the circuit and configurations. We will use a linear actuator and a few external electrical component to move the anchor joint of the AFO. Now, in order to move the anchor joint of the AFO by using a linear actuator, we must write a coding or programming in the Arduino IDE. This coding will be transferred to the microcontroller, and then it will be give instruction to the electrical components. All of the process of the methodology will be explained later on. Now we will look at the result and discussions. So there are 4 main sections for this part. The first one I will show to you the final design and the concept that have been selected. As you know that the designing of the L4 using CAD software, which is the CATIA, and the L4 will consist of 2 parts, which is the shank part and the foot part. A linear actuator will be used to move the anchor joint, which is to avoid muscle atrophy and muscle weakness. The second section is to conduct a FEA, which is the final element analysis. As mentioned earlier, there are 3 different parameters. The first one is the effect of material selections. The second one, the effect of different thickness, and the third and the final one is the effect of variable load. For the third section, will be fabricate the FO, which is by using 3D printer, and the material that I choose for this is the PLA, which is the polylactic acid. The final section is the IoT applications. So this IoT applications is important because it is used for the movement of the anchor joint. No MCU ESP3222 will act as a microcontroller that will give the instruction to the linear actuator and the other electrical component. We will look at the result of the first section, which is the designing of the AFO. The AFO have 2 main parts, which is the shank part and the foot part. The shank part is where the shank or cuff of the body part is rested when using the AFO. It can be seen here at the bottom image, which is I highlighted the shank part. The second part, it can be seen in the middle of the image, which is the foot part, which is where the foot is rested on a fixed position. The full assembly, which the assembly of the shank part and the foot part are joined together by using a bearing. It can be seen also there's a linear actuator to it. Now, the upper part of the linear actuator will be mounted on the shank, while the linear rod, where the part of the retraction and the extension happen, is attached to the back foot of the foot part. When the linear actuator retract or extend, a dorsiflexion or plantar flexion will occur in the foot. By doing this, muscle atrophy and muscle weakness can be avoided. Now we will move to the second part of the project, which is the finite element analysis. Shown in the screen here, there's the boundary condition both for the foot part and the shank part. The clamp area is at the back of the shank part for the shank part, obviously, and the distributed force is where the cuff or shank body part will be rested to when the patient is using this AFO. And the distribution, and for the foot part, the clamp area will be at the hole, as you can see, because this is where the bearing will be put, and this is where the movement of the ankle joint will be moved. The distributed force applied is on the foot part. Actually, the shank part will be the most critical because the FO will be used when the patient is on the back. So most of the weight have to be is transferred on the shank part, while the foot part is not a critical part because most of the weight is not on the foot part, only a few. So there will be no critical stress. There will be no critical stress happen. The first parameter that will be measured is the effect of material selections. As you can see, there are three types of material that have been selected in this analysis, which is the polylactic acid PLA, the ABS, and the nylon 6. But in this analysis, the constant parameter is the thickness, which is 2 mm, but the load applied for the shank part is 140 newtons, and the load applied for the foot part is 100 newton. Now, the final result to be observed from this analysis is the maximum bond mixture stress of all three materials, and also the maximum displacement of all three materials. Now, the mechanical properties that need to be that important for all the three materials is the yield strength. You may see in the table. However, when we look at the data that have been shown here for the shank part, ABS material have the highest bond mixture stress, followed by PLA and nylon for the bond mixture stress. However, for the displacements, ABS also have the highest, but followed by the nylon and the PLA. Although the value of ABS is very high, but it is still acceptable because the bond mixture stress does not exceed the yield strength of all three materials. And to put it clearly, all three materials can be used to fabricate the AFO, but the safer one might be the PLA. Why? Because PLA have the lowest displacement, although it have a slightly higher bond mixture stress, but it still can be acceptable. The same result can be seen here at the foot part, whereas the ABS have the higher bond mixture stress, followed by the PLA and nylon 6. However, for displacements, ABS also have the highest, but followed by the nylon and the PLA. It's the same as the shank part, which is the result of the bond mixture stress is acceptable, and all three materials can be used to fabricate the FO. But the most easy or the most easy to use might be the PLA. Now, we will look at the effect of different thickness on shank part. With material that involved in this section is only PLA. However, the thickness that will be used is three types of thickness, which is 2 mm, 4 mm, and 6 mm. The constant variable load applied is 140 Newton. We will look first at the shank part. Now, the graph shown that the displacements and the maximum bond mixture stress decreases when the thickness increases. This is logic because they have more, because when the thickness increase, when it can support more load applied, and when the load is maintained but the thickness is increased, then the bond mixture stress is decreasing as long as the same as the displacement. Now, it can be seen here in the static analysis in the left part, which is this is the stress, which is this is where the stress occur. Now, the stress occur at where the shank part is, where the shank body part is rested. It can be seen here that the stress, when the green color, it can be seen here that the green color into mm, which is higher, which is the stress is higher, is over there, but the green color is slightly changed to light blue when the thickness increase. Now, for the displacement, for the translational displacement part, we can see that displacement can occur at the front part of the sham part. Now the heavy green color is slightly decreasing when the thickness increase. To sum up, even if 2 mm is used to fabricate the FO, the volumetric stress is still acceptable because it does not exceed the yield strength of PLA. Now, we will look at for the foot part. The foot part we will use PLA, and we will use 3 different thickness, which is 2, 4, and 6 mm. But for the load is different. In the shank part, we apply 140 Newton. But for the foot part, we apply the highest the highest load, which is 100 Newton. As you can see here, the volumetric stress increases when the volumetric stress is high during 2 mm, but it decreases a little bit at 4 mm, but it rises back during the 6 mm. Now, this is quite logic because as you can see the static analysis here at the volumetric stress, which is the picture on the right below part of the slideshow. The stress occur near where the clamp force is. So with the value of the volumetric stress and the value of displacements, it can be seen here that the thickness play an important role to see that the stress is high or not, and to see whether that the displacement is high or not. So to sum up, it is safe to use 4 mm for the foot part, which is the lowest volumetric stress and the lowest displacement. The analysis continues by using different load apply. However, the same material will be used, which is the PLA. The same thickness will be used, which is 2 mm only, because in the previous analysis 2 mm can sustain without failure. The 3 type of load will apply is 140 Newton, 280 Newton, and 560 Newton. All of this data have been taken in the previous lectures. And when the load increases, the volumetric stress and the maximum displacement increases. Now this is very logic. However, all of this volumetric stress value is still acceptable and it will not fail. Now the third section is fabricating the FAO using 3D printer. As I mentioned earlier, the FAO consists of 2 parts, which is the shank part and the foot part. Both of the parts can be seen clearly in this picture. The foot part is on the left and the shank part is on the right. It is not joined together. It is not mounted together for now. The thickness chosen for this 6mm was used. However, the infill is only 50%. 2 types of 3D printer is used, which is for the foot part. It was printed using Flash for Guide 3, and the for shank part, the Creator and the 5+. The material for this both shank part and foot part is PLA. Now, for the fourth and the final section is the IoT application inserted at the FO. This feature allows the patient to control the rotation of the ankle joint. By controlling the rotation of the ankle joint, dorsiflexion and plantar flexion movement can occur. Now, when this movement occurs, muscle shortness and muscle atrophy on the calf muscle will be avoided. Component involved in this IoT application is the Node MCU SP32, which is a microcontroller, the most important part, and the second electric component is linear actuator, which will retract and extend to move the ankle joint. And lastly, the DC motor driver. Now, Node MCU32 will give instruction to the DC motor driver, and the DC motor driver will give instruction to the actuator by retracting and extending. Blink application software, which you can see in the middle picture here, is the interface that will be used to control the movement of the linear actuator. There's a video I will play here. Now, you can see that linear actuator retract when the button on the application is pushed. And then when the other button of the application in the blink is pushed, the linear actuator will extend back to the original place. Now this movement can be repeated many times as the patient wants. As a conclusion, it is safe to say that all three objectives of the project have been achieved. The customized adjustable ankle FO to see was successfully designed using CAD software, and the FO consists of shank part and foot part, and the FO was successfully undergo finite and with different parameter. The value of the maximum stress and the value of the wall maximum stress and the displacement value for all materials is acceptable, and it does not exceed the yield strength of each material. All thickness can be applied for both shank and foot part, for which we can see earlier that it does not fail. And even if the higher load of 560 Newton is applied to the shank part, it still does not fail. However, if we want to increase the load, further analysis have to be taken. PLA material was chosen to fabricate the FO using 3D material. And lastly, the adjustable FO was successfully working with the integration of IoT applications. With this movement of the ankle joint that have been taken, muscle atrophy and muscle shortness can be avoided. To end this, I would like to say a few recommendations that can be made in this research in the future. The first thing I would like to say is that a better prototype can be made by using a different electrical component that can be used to move the ankle joint. Thirdly, an analysis can be made by increasing the load applied, so which we can see that at what load that the FO will fail. And that is all for me. I would like to thank you to my supervisor and to my panel. If there's any question, you can contact me through my email as shown in the slides. Thank you and have a very good day.